At this point in time, we've seen a lot of convergence tests. So now we need to figure out how we know which one to use for a given series. In this video, I'm going to review all of the convergence tests, as well as give some tips and tricks about when might be the best time to use each of them. Bearing in mind that our goal is to decide whether or not a given series converges absolutely, or diverges, our mission is then to choose a test that matches the structure of the series in question. It's always a good idea to start with a divergence test. This test tells us that if the limit of the terms of the series is not 0, then the series diverges. If the limit is 0, it's inconclusive and we need to move on. But if we can automatically conclude that it's divergent because its terms don't go to 0, that's a quick place for us to start. Once you've completed the divergence test and convinced yourself that your series has a chance of converging, it's time to ask yourself if it is an identifiable series. At this point, you should have 3 kinds of series that you can fairly easily identify: geometric series, telescoping series, and p-series. Let's look at each of those. A geometric series is going to be of the form a times r to the n, and that will converge if the absolute value of r is less than 1, but diverge otherwise. If your series has terms that are separated by a negative sign, this might be a clue that it's telescoping. That won't always be the case, but it's worth investigating. Telescoping series have partial sums that are easily turned into a closed formula. In order to determine their convergence, then, you just have to take the limit of the partial sums. Some of the most useful and ubiquitous series are the p-series. So now you need to see if you can identify one of those. If your series terms are of the form 1 over n to the p, perhaps after some simplification, then you'll know that it converges if p is bigger than 1 or diverges for p less than or equal to 1. If it's not identifiable, then your next question is, can I compare it to an identifiable series? We have 2 ways to do that, using the term-by-term comparison test and also using the limit comparison test. To use the comparison test, you're going to choose a series whose behavior you know, and you're going to compare your existing series to it. If you chose a convergent series and your current series is smaller than that, then you know the current series converges. If you chose a divergent series and the current series is larger than it, then you know the current series diverges. The comparison test tells us that if you're smaller than a convergent thing, you're also convergent. And if you're bigger than a divergent thing, then you're also divergent. While the comparison test compares the sizes of the terms of 2 different series, the limit comparison test looks at the ratio of the pieces of each of those series. If that ratio has a finite limit, then that means that one of those series is behaving just like a multiple of the other. In other words, if one of them converges, the other, which is behaving like a multiple of it, must also converge. If one of them diverges, then the other one has to diverge as well. When you've gotten as far as you can by recognizing known series or comparing to known series, it's time to inspect a little further. Our next question is, do the signs of our series alternate? In this case, you're going to use the alternating series test. While in general, it's not sufficient for the terms of a series to go to 0 in order to guarantee convergence, for an alternating series, that is the case. If we have a series whose terms alternate between positive and negative, and the terms of that series are not increasing and their limit is equal to 0, then we know that that series converges. So we're now at a place where our series isn't a familiar one. We don't know how to easily compare it to a familiar one, and it doesn't alternate. We'll begin seriously inspecting the terms of our series in order to figure out what test is next. If that series contains factorials or exponentials, that might be a clue that we want to use the ratio test. The ratio test is one of the tests we have that determines if a series begins to act like a geometric one when n gets large enough. In order to perform it, you're going to look at the limit as n goes to infinity of the ratio of the n plus first term over the nth term. If that limit is less than 1, then you have absolute convergence. If it's greater than 1, it's divergent. If it's equal to 1, you've got to do a little bit more work. You can also inspect the terms of your series to see if there are any things raised to the nth power. In that case, you might consider the root test. Like the ratio test, the root test is giving us a sense of whether or not our series eventually starts to behave like a geometric one. Here we're going to look at the nth root of the nth term. And then we'll take the limit as n goes to infinity of that quantity. If that limit is less than 1, once again we have absolute convergence. If it's greater than 1, we have divergence. If it's equal to 1, we need to do some more work. We've got one last test to look at. This one doesn't necessarily need to be done last, but it can often be one of the more complicated ones, so I've held it to last. Here we're going to examine whether or not the terms of our series look like they could belong to an integrable function. If that's the case, we're going to use the integral test. The integral test tells us that if our series corresponds to a real-valued function that we can integrate, then the series converges if the integral from 1 to infinity of that function f of x also converges. And similarly, if the integral diverges, so does the series. We'll wrap up with a table that hopefully synthesizes some of what we've talked about here. If you have a series whose terms don't go to 0, you can apply the divergence test immediately. Next, you should look for familiar patterns, a times r to the n, or terms that appear to cancel, and consider a geometric or telescoping series. If it's not one of those, you can look for nth powers or polynomials, in which case you'll consider using a p-series test or a comparison test. If your series contains simple rational forms, a limit comparison test might be an appropriate tool. If the signs alternate from positive to negative, use the alternating series test. If you see factorials or exponentials, you're going to consider a ratio or a root test. And then if your series appears to look like a function that you know you can integrate, you can always use the integral test.